Hello and welcome to NCC Group's Cryptopals guided tour. My name is Eli, I'll be your guide. In this video, we're going to be looking at Challenge 2 from Set 1. This challenge involves implementing XOR on byte strings. That's bitwise XOR naturally. And we're given two input strings here, and the XOR of them ought to produce the given output string here at the bottom. Now this is a fairly straightforward challenge once you get the right idea for it. However, there's a lot of different ways that you could do it. And what I would like to do to start out is show you 4 different reasonable Python implementations of the solution to this problem, and then we're going to benchmark them and see which one's the best. And this is going to be valuable because we're going to be using this function a whole heck of a lot in the rest of these challenges. And so making sure that it has good performance is absolutely critical. So let's go ahead and see how we might write this. First off, in order to do the required XOR operation here, we're going to need to iterate over both of these strings together performantly. And so that means taking this byte and this byte at once, this byte and this byte, and so forth. And there are 2 ways that we might reasonably do that. Let's look at both of those and see how they fare. We're going to say A, we're just going to call the 2 byte strings A and B. A equals bytes.fromHex on that, B equals bytes.fromHex on this. And the XOR of these should produce this target value, which we will copy in once we are able to check it against something. So now to begin here, let's take our first iteration method. And this is just going to iterate over all the indices in these. So it's going to figure out which of these is the shorter string and iterate over a range and index into both byte strings for each value in that range. Here's what that looks like. And we're not going to print these out or anything because printing to standard out can really mess with your timings. It can have super inconsistent latency. And so if we want to benchmark these, then we have to avoid doing that. So instead, we are just going to evaluate a trivial expression on both of these values. And Python is generous enough not to optimize that out for us so that we can actually get some sense of how this performs. So that's our first function. And this one is just going to iterate over the zip of these 2 strings. For byte 1, byte 2 in zip A, B. And zip is a little functional programming style function here that allows you to pass some iterables and basically get exactly what we want, which is the first element of each of them, then the second element of each of them, and the third element of each of them, and so forth, all grouped up together. And this is super convenient in a ton of situations. One thing to note is that this only goes until the shortest one is exhausted, so if they're not of equal length, then it will discard some of the tailing end of the largest arguments. That's not super important here, but it's just something to be aware of. So anyway, let's get some timing information on these. Now, if we wanted to just time a single execution of them, for example, if we had something that takes a really long time to run, we're curious how long it takes, we could do something like this. However, what we want is accurate timing data, and in order to do that, we want to take a lot of samples. So let's do this, which uses the built-in timeit library and runs the function a bunch of times, collects timing data on it, and then takes medians on that data to give us super accurate results. And here we go. 1.61 of whatever these are. Microseconds, maybe? Sure. So anyway, 1.61 for our first method, which you will recall is the one that iterates over the indices. And then now we'll try the zip one. We'll see how that fares. Well, that's interesting that it's using means. I recalled this using medians, but I guess I was wrong about that. Anyway, we see that the zip method is much faster. So that's the one that we're going to use. It's also the one that produces more readable code. So that's very nice as well. Now that we have that sorted out, let's look at how we might implement XOR. This first method is just going to I don't want to get people confused. This is not a class method. This is just method as in algorithm. But this first method is going to take a byte string and build it up one byte at a time. This is probably, you might call this the naive method for implementing this. It's certainly the most obvious to a lot of novice programmers, I think. And we'll see how it fares against the rest of the options in a moment. The caret character here represents XOR on integers. And bear in mind, when you iterate over a byte string in Python, what you iterate over are individually integers. This is actually something that a lot of people don't realize. If you do, for example, it prints out the actual ordinals corresponding to each character. And that's because bytes are just numeric values. When they're grouped like this, Python pre-prints them. And for the printable ones, it prints out their ASCII equivalents. But internally, of course, they are represented as, bytes. So anyway, we're able to treat them as integers here and XOR them. And then the actual bytes function here takes an iterable as input. And so we have to construct a list of length 1 here in order to construct a byte string of length 1. And one optimization we can make, I like writing this with a list because it's more readable, because you have 2 different kinds of brackets instead of 2 of the same kind. But Python actually constructs tuples about 10 times faster than lists. And so doing this, which creates a length 1 tuple, you have to put this trailing comma here so it knows that this is a tuple and not just a set of parentheses. But doing this should give a tiny, tiny little speed up. So we're going to do that just to make the competition fair here. So let's do that. And then we're going to return our result. Our second method here is going to work a lot like this first one, except instead of building up an intermediate series of byte strings, we're going to use a list as our intermediate result, and we're going to append to the list and then convert that to bytes at the very end. So this will look otherwise very similar. One advantage of this is that we don't need to construct these intermediate data structures, which probably is good for performance. Our third option is going to use a generator expression, and it's otherwise going to be very similar to the logic of this one. So we're going to join on the empty byte string. This is basically an idiomatic way in Python of concatenating a bunch of values that are stored in an iterator of some kind. So this is not that different from this, except obviously that it's written out in one line, which is nice. That's one thing about these iterators, these generator expressions, is that they can be extremely terse, sometimes to a fault, actually. It's very easy to produce unreadable code with them, but used judiciously, they can really, really clean up your code. So there's our third option. And our fourth one is going to be sort of similar to this, but using the idea of generating a bunch of integers and then converting them to bytes at the end. So as this is to this, so this will be to this. And in my opinion, this is the one that definitely reads the best out of all 4 of these. So here we are. Let's take some benchmarks. It's very exciting, wouldn't you agree? Our first possibility here takes 4.6. Our second one, 2.32, and that completed very quickly. Oh dear. What did I do here? Oh no. Pardon me, I actually have a small mistake in this one. I misplaced a parenthesis here. That should be like that. So now let's try that again. All right, and that takes 4.65, so that's actually it's worse than XOR 1. But none of them even come close so far to XOR 2 here. Now let's see how XOR 4 fares. 2.28 compared to 2.32. Now that's quite close for both of these. That's close enough that I would say it's worth just going with the more readable one, which also is marginally faster here and otherwise comparable. We're going to go with XOR 4. That's going to be the function we use, but let's do one more round of competition between these two, just for kicks. Hey, there we go. All right, undefeated. So let us take our XOR 4 function and we will write it just like that. Add some type annotations. And there we go. Oh yeah, we need to make sure the output of this is correct. So let's try that really quick. That looks right to me. I don't think we even need to check that against this. I think it's pretty clear that that's turning out to be what we want it to be. Now, one thing that might be useful to us is if you go back to the help for zip here, you notice that it takes any number of iterables. And it would be neat, in my opinion, if we could do the same thing for bytes XOR. Just take an idea from that. So let's we'll retain this 2-argument version, which if we ever have a 2-argument XOR in a tight loop somewhere, then we can just import this and use it directly. But we will wrap this in sort of a convenience function. And this convenience function is going to add a handful of features that might be nice for us. Actually, the only feature it's really going to add is the ability to accept a variable number of arguments. But I'm also going to add in a couple other things here, which are convenient. And just to talk about this for a second, quiet is going to give us debug output, which is super useful down the road if we're trying to troubleshoot a problem in one of these scripts. And then check lens is going to add in an optional length check. The reason I'm doing that is because if we read the exact text of the function, it does specify equal length buffers. Personally, I would prefer to retain the option to have them have unequal lengths and have it be treated basically how zip treats that case. I think that that's more flexible and more useful, although I will admit that there's slightly less error checking going on there. But just in order to actually, hew to the text of the function, to the text of the challenge, we are going to add the option to make this execute exactly as specified. So let's add those in there. And we're actually, spoiler alert, we're going to end up passing those through to our backend function. So let's go ahead and implement them back here right now. That's annoying. So that this, by the way, is the symbol for XOR that is generally used, in case you're not familiar. And due to Boolean short-circuiting, if check lens is false, then this will not be evaluated, which is nice because checking the len of a string can be an operation with a non-negligible cost. So this is very nice because this adds virtually no overhead. In the case of the default values being used here, both of these just involve evaluating one Boolean and then skipping these blocks, which is almost negligible in cost. So that's very good for performance. Now let's go fill in our front-end function here. Now using assertions is sort of a loaded topic in Python. Some people would say you shouldn't do this at all. The basic issue is that there is a flag that you can pass to Python, -o, you see it right here, that basically removes assertions completely. And so if you ever had branching logic in your Python script, then this would be really, really problematic, because if the script could somehow be coerced into running with the -o flag, then your branching logic would change. And if that has to do with, for example, input validation, then that's really, really bad. So a lot of people would say that asserts do you as much harm as good. I personally think that's an overstatement, but it certainly is true that you should only ever use them for checking invariant properties in your code. And whenever you're doing any sort of validation check, you should do that in other ways, typically through raising exceptions if something is not looking copacetic. But in this case, I think it's reasonable to have a quick assertion here, particularly because on the very next line, we rely on this assumption. And so if you passed no arguments, you would get a cryptic error that doesn't actually tell you what's wrong. So I think this is just a little bit more usable. And the assumption also is that if you're calling this function, then performance is not of the utmost importance, because if it was, you'd call this one. And so the cost of this len check is probably unimportant here in context. And so there we go. We just take the first argument, then we iterate over the rest of them, compute XOR on each of those in turn, and we get our final result. And now if we are running the script directly rather than importing it, then we will run a little bit of code that makes sure that this challenge is actually being completed. And we'll do quiet equals false here just so that we can see the arguments and so that we can see our nice little, XOR symbol. And this is nice. We're going to print out the result in its raw form first and then its hex form second, because we're given the target value in hex. And so it would be nice to be able to visually confirm that that matches our expectation. And then we're also going to check it here explicitly. And there we have it. This should just about do it. So let's run it. Let's see if it works. And there we go. It worked. So that's challenge 2 solved. Thanks for watching. I hope to see you in the next one.